Hey everyone, welcome back to my YouTube channel. In this video, we'll explore an important topic that every engineering student and professional needs to master: numerical calculations. In engineering practice, most of our calculations are performed using handheld calculators or computers. But here's the deal: it's not enough to just get a number. You have to make sure your answers are reported with the right level of accuracy, and that means using the correct significant figures, checking for dimensional consistency, and rounding your numbers properly. Let's start with dimensional homogeneity. This principle tells us that every term in an equation must have the same dimensions or units. What is a term? A term is a single part of a mathematical expression or equation that can be a constant, like number 5, a variable, like letter T, or a combination of both, possibly with coefficients, like 1/2 at squared. In an equation, terms are separated by plus or minus signs. Take this classic kinematic equation. S is equal to Vt plus 1/2. At squared, we can identify three terms. S is the left-hand side of the equation, or the position. Vt is the first term on the right-hand side, or the velocity times time. 1/2 at squared is the second term on the right-hand side, or 1/2 times the acceleration times the square of time. So, each term in this equation represents a quantity with dimensions. According to the principle of dimensional homogeneity, all these terms must have the same dimensions. In SI units, S is position in meters, V is velocity in meters per second, T is time in seconds, and A is acceleration in meters per second squared. So let's break it down. Vt is meter per second times second. Cancel the second and left with meter. 1/2 at squared is meter per second squared times second squared. Cancel the second squared and left with meter. Every term is in meters, so the equation is dimensionally homogeneous. Now, let's say we solve this for acceleration. A equals 2 times s over t squared minus 2v over t. In this form, the terms would have units of A is meter per second squared for the acceleration. S over t squared is meters per second squared. V over t is meters per second over second, simplified to meters per second squared. So again, all terms are in meters per second squared, confirming dimensional consistency. Always remember, dimensional homogeneity helps us check if our equations and algebraic manipulations are valid. Next, let's talk about significant figures. These indicate how accurate or reliable a number is. Let's take some examples. The number 4,981 has 4 significant figures. But how about 23,400? It's tricky. That could mean 3 significant figures. That could be 2, 3, and 4. 4 significant figures. That could be 2, 3, 4, and 0. Or 5 significant figures. That could be 2, 3, 4, 0, and 0. To avoid this confusion, we use engineering notation, which expresses numbers as powers of 10, such as 10 to the power of 3, 10 to the power of 6, or 10 to the power of -9. For example, if 23,400 has 5 significant figures, write it as 23.400 times 10 to the power of 3. If 23,400 has 4 significant figures, write it as 23.40 times 10 to the power of 3. If it has only 3 significant figures, write it as 23.4 times 10 to the power of 3. Now, what about numbers less than 1? Leading zeros don't count. For example, 0.00821 has 3 significant figures. Write it as 8.21 times 10 to the power of -3. 0.000582 can be written as 582 times 10 to the power of -6, or 0.582 times 10 to the power of -3. Here's a tip for you, buddy. Expressing numbers in powers of 10 avoids ambiguity and maintains clarity. Let's now go over rounding off, an essential part of reporting your final answer correctly. Here's the rule. If the digit after your rounding point is greater than 5, round up. If it's less than 5, round down. And if it's exactly 5, there's a special rule. Let's take some examples. Round 3.5587 to 3 significant figures. The fourth digit is 8, so it becomes 3.56. Round 0.5896 to 3 significant figures. The fourth digit is 6, so it becomes 0.590. Round 1.341 to 3 significant figures. The fourth digit is 1, so it becomes 1.34. Now, the special case, if the number ends in 5 and the digit before the 5 is even, don't round it up. If odd, round it up. Examples. Round off 75.25 to 3 significant figures. The 2 before 5 is even. It becomes 75.2. Round off 0.1275 to 3 significant figures. 7 is odd. It becomes 0.128. And round off 0.2555 to 3 significant figures. 5 is odd. It becomes 0.256. This rounding method is used to avoid rounding bias over many repeated calculations. Why do some people or calculators not follow the even-odd rounding rule when rounding 5? That rule does exist. It's called round half to even, also known as banker's rounding. But here's the catch. There are multiple rounding rules and not all people or tools use the same one. First is the round half up, or the common rule. This is what most people learn early on and apply by default. If the digit after their rounding place is 5 or higher, round up. Example, 2.25, it becomes 2.3, and 2.35, it becomes 2.4. This method always rounds 5 up, which introduces a slight bias toward larger numbers over time. Second is the round half to evens, or the banker's rounding. If the digit after is exactly 5, with nothing following, or just zeros, then round to the nearest even digit. Example, 2.25, then it becomes 2.2, because 2 is even, and 2.35 becomes 2.4, because 3 is odd round up. This reduces rounding bias and is especially important in financial, statistical, and scientific computations. Why don't most calculators follow the even-odd rule? Because most basic calculators and even many scientific ones are programmed to use round half up, the simplest and most intuitive method for the general public. To follow round half to even, the calculator would need a more advanced setting or mode, or be part of software like Excel, Python, MATLAB that supports different rounding options. Examples, in Microsoft Excel, the round function uses round half up, but round.math or custom rounding functions can be made to use round half to even. In Python, it uses round half to even by default for round. So, why does engineering prefer the even-odd rounding? Because over many repeated calculations, always rounding 5 up adds bias. In engineering, we need neutrality, consistency, and statistical fairness. So, round half to even is a more balanced method, especially when working with many significant figures, running simulations, and doing scientific analysis. If you're teaching or presenting, you can note both methods and clarify when and why round half to even is preferred. Important reminder, always ask your instructor or professor what rounding rule they expect you to follow. Different schools or departments might have different preferences, especially when preparing technical reports or solving exam problems. Have you ever wondered why your final answer in a long calculation seems slightly off, even when you think you did everything right? One common mistake that causes this is rounding too early in your calculations. Let's break this down. First, don't round your intermediate values. Store them exactly either in your calculator's memory or carry them with full precision if you're solving by hand or using a spreadsheet. Only round off at the very end when you're ready to report your final answer. Why does this matter? Because small rounding errors, so like 0.0001 here, 0.0005 there, may seem harmless at first. But when you're doing a series of steps, especially in engineering or scientific computations, those small errors add up. In real-world engineering, accuracy is critical. A tiny miscalculation due to premature rounding might result in incorrect loads, unsafe dimensions, or even structural failures. Second, typically, we round our final answers to 3 significant figures, because that's about the level of precision we can realistically expect from measurements like geometry, forces, and loads. For example, if you're working with a force value derived from a measured weight and acceleration, your instruments likely don't give you 10 decimal places. So rounding to 3 significant figures is both practical and meaningful. So remember this formula for success: full precision, full solution, round only at the end. To sum it all up, dimensional homogeneity ensures equations are physically meaningful. Significant figures reflect the precision of your measurements. Rounding must follow proper rules to maintain accuracy, and intermediate results should never be rounded. Only round at the end. These may seem like small things, but they make a big difference in engineering precision and professionalism. If this helped you understand numerical calculations better, give this video a like. And don't forget to subscribe for more engineering tutorials. Drop your questions in the comments. I'd love to help you out. Bye.